Welcome back. Today I'm doing uh, 310 minimum height trees. A tree is a undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. Given a tree of n nodes, this is a tree. The tree is an undirected graph. Okay, so the edges don't point to each other. Given a tree of n nodes labeled from 0 to n1 and an array of n minus 1 edges, where edges is pair of a nodes indicates that there is an undirected edge between two nodes A and B. In the tree, you can choose any node of the tree as the root. When you select a node X as a root, the result tree has some height h. Among all possible rooted trees, we'll have to return the minimum height tree. Those with minimum height, return the list of all minimum height trees root labels you can return. So this is a tree with 4 nodes, and when we use 1 as root, that's when we get a tree, minimum height tree. Here, using root, there is the height is 1 or 2 if you, no, height is 1, no? 1. There is only one level below root, and these are leaf nodes. In this example, we have 6 nodes, and we get 2 minimum height trees. Well, when we use 3 or 4 as roots, we get something like this form. So yeah, I have some notes with me from last time. Basically, what I have to do in this problem is, in order to solve this, is something called topological sort. How many minimum height trees can a graph have? How many minimum height trees can a graph have at most? So yeah, the idea is to basically find the leaf nodes, and for example, this is the Here 0, 2 and 3 are the leaf nodes, so we get rid of them. We are left with 1 only. Because maybe because well, we know that leaf nodes are the end of the tree, are there, they are at the end, so there's not going to be another, like there will never be another level below them. So if we just get rid of them, uh, if you just get rid of them, I don't know, like here 0, 1, 2, 1, 2, 3. Can I let me see it in, I don't know, draw. So we have this tree with the 1, 2, 3, 4, 6 nodes, and 1, 2, 3, 4, just forget about it. But yeah, if we use a 0 as root, then 3 comes between 0 and these three roots, and suddenly we have a height of 4, right? I kind of found this problem very okay. Yeah, so we need to well, I don't know, very minimum height tree. Okay. If we have we are given an indices, we don't need to create actual tree. We first of all we need to create an adjacency list. Maybe let's begin with that. Integer of list of integers, but it's actually an array. Graph is new. For I is smaller. Actually, I saw a very good diagram here. Yeah. So we keep eliminating these outer leaves and until we narrow down to 1 or 2 nodes. Okay. While I is smaller than n, it's I plus plus and graph at I new array list. Okay, next. Graph for edges for each edge in edges. Graph edge the 1 0, maybe add 1 you have to do the same for let's just see. Result new array list and good will return okay system.out.println h I mean graph generic array creation array new maybe array list list or maybe I need to do type conversion. Well, I'm just looking for a array of list array of list how to create array of list in Java. Okay, I'm not supposed to use generics. Aljava util list. What's that mean? One. What does that mean? Y is content of the graph not getting printed. Vice constants of the group. Okay, I'm supposed to access each index at a time. Got it. Got it. System.out print ln graph. By the way, I'm recording. I don't know, I just today this problem is very hard. Yeah, okay. I got my adjacency list that represents my graph. So 0th node is connected to, well, there is an edge between 0th node and first node, and then there the first node is connected to 0th node, second node, and third node, right? So the first node is connected to all the other nodes in the graph. It's central node, and then second node is only connected to first node. Same with third node. Yes, fine. This is what we wanted. Now I think the next step is to in degree, maybe silk names nodes. 0 has a degree of 1, 1 has degree 3, 2 has degree of 1, 3 has degree of 1. Can I somehow use this information? Let's int degree, it's a list, degree is new int n. Well, for int I is 0, I minus, when I run this till n, and degree I is equal to graph I dot size, because it's essentially a list, so we are getting the size of each node in the list, which is actually telling us the degree of that node. Okay, what's the next step? Maybe queue. Now to get the leaf nodes, queue queue of integers, so queue is new so I'm gonna add all the nodes having 1 degree to my queue. Right, so let's just do this within if graph if degree I is equal to is equal to 1, q dot offer I is basically a node. Okay, now what I can do is I can run a depth first search while q is not empty. While q is not empty, I'm gonna int leave is q dot pull so our queue will have our queue will have zero, 2 and 3, because these three nodes are having a degree 1. Now what I'm going to do with these leaves, what's my degree 1 1 2 3 1 and 1, and my leaves just let me get the size of the queue. Queue dot size, and I is equal to 0, and while I is smaller than size, I plus plus, yes. Heat up all the nodes until all the leaf, basically idea is to eat up all the leaves at the same time. For a path and graph of n nodes find which by stability. Suppose we don't know n, nor do we have random access of the nodes. We have to traverse it. It's very easy to get the idea of 2 pointers, one from each end, and move at the same speed when they meet, or they are one step away depending on the parity of n. We have the roots we want. This gives us a lot of useful ideas too. For a tree, we can do similar things here. We start from every end. We start from every end, and that's what our leaves nodes are, doing. Let's get this leaf node. Leaf is q dot pole. Now I've got one end. Eyes. No. Graph. And I iterate leave should give me a list. if zeroth node is connected to 1, so we'll have 1. What do we do with this one? What do we do with this one? Correctly, we can use the thing. We start from every end by, and we mean vertex of degree 1, aka leaves. Let the pointers move the same speed. When two pointers meet, we keep only one of them until the last pointers meet, or one step away we find. It's easy to see that the last two pointers are from two ends of the longest path. It's easy to see last two pointers are from the two ends of the longest path in the tree. The actual implementation is similar to BFS topological sort. Remove the leaves, update the degrees of inner vertices. Hmm. 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 The time comes. While C and T is greater than 2, what does that mean? It's initially set to n. Then size is equal to leaves dot size. When degree becomes 1, q dot offer that node. Yes. And whatever is left in my queue at the end, I will add it to my final list. So this is not really useful because queue never becomes empty. What is CNT? CNT doing your CNT variable tracks the number of active nodes remaining in the graph during the BFS leaf removal process. Why it's essential? Remove all current leaves. Current peels layers of leaves from the. We stop when only one or two nodes are left. Okay. Well, yeah, this kind of makes sense when I think about this. So size obviously represents the size of the queue, and it also means that I think it also means that okay, size is the number of nodes we are cutting off from the tree. So if there are n number of trees, n number of nodes in the tree, and minus size, then yeah, okay, so that okay. Maybe nodes left is better name. Nodes left. Well, initially there are n nodes, and while nodes left are greater than 2, size right. Okay. if n is equal to n is smaller than 2, return interesting. Okay, got it. Okay, this was my second time solving this problem. Still, I mean, I will not be able to do it if you just give the same problem. Yeah, so if you give me the same problem in 30 minutes, again, I won't be able to do it. But okay, I got a little more closer to understanding the what's really happening here. Maybe if I like I did this thing last time where I actually dry run this whole thing on the paper. Yeah. Okay. Next problem. Just watching my last attempt on this problem, and I was very close to the solution. I was very close to the solution within 15 minutes of the video, but I just messed up in implementation. So it says the problem can involve monotonic stack. The last time I did this problem, I didn't know about what they are, but now I do. So given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. I think we can solve it either using 2 pointers or by keeping a stack. 2 pointer solution is simpler in my opinion. Well, it's we need a left pointer set to 0, and then we need a right pointer set to height length -1. We also need 2 extra. We need a left max that will keep track of the right max. These two will keep track of the maximum, the max. What is it called? Bar. Yeah, the max height on either side. Right and left. And here while left is smaller than right if height left is smaller than or equal to height right. If the 0 is smaller than or equal to 1, then we check if height left is greater than my left max, greater than or equal to my left max. Well, initially it will be equal, so maybe this is right. If it is, then well, left max, we update the left max to current pointer, else I just use the difference between okay, here this is 1, so a new left max will be set, and this is 0, 0 here, this is 0, so here 0 minus 1, my 1 minus 0, or 2 left max. Okay, let's say in units 0 units is equal to difference max minus my current height left, and I'll do the same thing with, just can copy this, well, this is just an else, don't need this. If height right move left, if height right is greater than left right max, then set my new right max, else give me the difference between right max and current right, and move my right pointer. Return units. Maybe let's try run this. We get 1 unit less. We're getting 1 unit less, so 6 units also. Right, not right, Max. Now we're getting 1 unit extra. Right. God, what am I doing? Okay, I want to look at stack-based solutions. Stack, stack, stack. Keep max height on both sides. No. 2 pointers. You know, it's doing the same thing I'm doing. Event-based monotonic stack solution for trapping. Rainwater can only be trapped when a lower bar is enclosed by a taller bar on both sides. Instead of checking every position repeatedly, we can wait for the moment when a right boundary appears that completes such a container by scanning the bars. Monotonic decreasing stack. The stack keeps bars in decreasing height. When a taller bar appears, it signals that a container is closed. The curved bar represents the bottom of a valley. Okay, I will look at this one later.